Hey everyone, welcome to another one of our fabulous lessons online. We are looking, hopefully you got the notes in front of you or you have a way to look at them. So this is from your Springboard section 25-2, and we are looking at inscribed angles this afternoon. So there's the definition. Let me just get this a little bit nicer for you. Okay, so if you're keeping track of your definitions, you can add this to your definition page, but we're going to talk about inscribed angles and the relationship between their arcs. Last time we were together, we had central angles, and central angles had a special relationship. Do you remember how central angles are related to the arcs they intercept? Hopefully you said that they are congruent in measure, because that's what we looked at last time, that central angles are congruent to the arc measures that they intercept. So inscribed angles have a little bit different relationship, and we'll look at that theorem right down here in the box. By the way, this is from a different book, so these theorem numbers do not correlate at all to Springboard, and you could call it the measure of an inscribed angle theorem. That makes you happy, but these are your theorems in these little boxes, and you can put those on your theorem paper. So you can look at our angle. Let's look at our angle here. Let's just label this A, B, C, and you can see the arc that we are focused on, the intercepted arc lies on the interior of the angle. So here is the intercepted arc there. So that's the relationship we're going to look at today. And inscribed, we have talked about inscribing a circle inside of a polygon. We had talked about inscribing a triangle inside of a circle. And the thing that you need to remember is that when we're inscribing something inside the circle, is what we're going to really look at today, is that the vertices of that polygon are going to be on the circle. So when you're inscribing, you are on the circle with the vertices. So when you hear the word inscribed angle, the vertex has to be on the circle. Now, normally I would walk you through an exercise like this in class, but since we don't all have we have a straight edge, but we don't have a way to measure our angles. You guys don't have your protractors with you. I'm going to tell you to come down here and let's look at letter 1B. 1B is an easy way to look at this relationship together. So here's what I want you to notice. We have got angle ABC is our inscribed angle, and they show it to you as part of a triangle. And that's super important because you're going to notice that it's a right triangle. And not only that, is that the diameter is the hypotenuse. And that's super important because if you highlight this inscribed angle that's 90 degrees, you're going to notice that it intercepts a semicircle, right? So you guys know that the right angle is 90 degrees, right? We've got 90 degrees here. And you already know that a semicircle is 180 degrees. So that should help you out with the understanding of this relationship, right? So that you can tell that the inscribed angle is half the size of the arc that it intercepts, or you could say the arc is twice as big as the inscribed angle. The way it's written in this theorem, it says if an angle is inscribed in a circle, then its measure is going to be half the measure of its intercepted arc. And I like the drawing that they have here for us. It's so nice to have a picture. We don't have to make it ourselves. So let me just put some numbers on this picture to just give you the idea so you can see what we learned yesterday and what we're learning today. All right, so let's say that this arc AB, that looks like about 80 degrees to me. Let's call that 80 degrees. So you know from yesterday's lesson that this central angle, angle ACB, would have to be how big? Yeah, it'd have to be exactly the same. It would have to be that 80 degrees. And then the inscribed angle with this theorem should be half that measure. So this should be 40 degrees, angle ATB. All right, we're going to go ahead and head down to number 1. And this says find the measure of the intercepted arc. These pictures are pretty simple, but you're going to get some, of course, because you're in honors, that are more difficult. So if you need a highlighter or a marker or something and you want to highlight the angles and the arcs that they intercept, some of the pictures will get a little more intense. But for right now, let's just highlight AC. So how big, according to our theorem, would AC have to be? Well, double in size. So this would make AC 140 degrees, 70 times 2. All right. Looking at letter C, we're looking for arc ADC, and that's a major arc. There it is. So we take that inscribed angle and just multiply it by 2. So 98 times 2 is 196 degrees. And that makes sense because you can tell that this arc is bigger than 180 degrees, right? Because it's going around more than half the circle. And not that all your pictures are always drawn to scale, but this one looks pretty good. All right, number 2, find the measure of the inscribed angle. So now we're going the other direction. Angle B would have to be how big? 60 degrees, half of that 120. And now this one, we've got a picture, it's not as clear, so let's focus. Angle EFG. We are looking for EFG. And look where it intercepts. So if you want to highlight this one, here's EFG. And that's the same as letter B over here, right? Because it's intercepting half the circle. So that's our right angle, or it's 90 degrees. And then the last one, angle PQR. I'm sure you can tell me how big that angle is. Half of the 48, which is 24 degrees. All right, let's go to the next page. The next page, we finally get something a little bit more challenging. I'm going to give you a moment. Let's take a look at it together real quick. The star divides the following circle into congruent arcs. So the congruent arcs that are divided by this star, these are all congruent to each other. So keep that in mind. Find the measure of the angles that are part of the star. So they're actually looking for the measure of the angles that are the points of the star, excuse me. So they're looking like for angle 3 here, 7, 4, 1, 5, 2, and 6. But they're all the same. So go ahead, give it a try. All right, how did that go? So let's take a look at what we should have done. You have, if you counted them, there are actually 7 arcs here. So the first thing you should have found out is how big is each one. So you're going to do 360 degrees divided by 7. And that's going to give us, I think it's 51 point something. Yes, 51.42. And I would just leave that in your calculator on the side here, right? So each one of those, but when you look at the angle, let's look at number 3. I don't know why. Angle 3 is just grabbing me. That means you're looking at 1, 2, 3 arcs. So we're going to multiply this number by 3, and you can just do that on your calculator. And I get 154.285, yada, yada, yada. Now here's the thing. That is encompassing this whole entire length of that arc. But remember, it's not equal to the inscribed angle. It's half of that. So we're going to divide by 2. And so your final answer for angle 3 is 77 degrees. I really got like 77.14, but we can round it. Pretty good, huh? Fun stuff, right? All right, look at number 4. I'm going to let you read it and come up with the answers for there's three angles that they're asking answers for. So go ahead and read that. All right, so let's take a look at this one. We are looking first and foremost for angle ABE. Here's A, B, E, and it intercepts this arc. So the arc is 90. So the measure of angle ABE is going to be half of that, which is 45 degrees. And then they ask us for angle ACE. Look at this, my friends. It intercepts the same arc. So guess how big that is? Well, it's still half of the 90. So it's also 45 degrees. And finally, they ask us to find the measured angle ADE. Intercepting the same arc again. So the measure of angle ADE is equal to 45 degrees. Maybe you're noticing a little relationship here. It might help you out with number 5. Go ahead and find the measure of angle C in number 5. All right, so angle C, did you say it's 55 degrees? Yeah, hopefully you're seeing this relationship happening. Angle B is intercepting this arc AD, and angle C is intercepting the same arc. So they must be the same degree measure. And that's actually another theorem that we have today. If two inscribed angles of a circle intercept the same arc, then the two angles are congruent. So you can see from some of these problems that the diagrams that you're going to get are going to get a little intense. So keep those highlighters and colored pens ready. They'll be super helpful for you. All right, last topic, last page of our notes is we're going to look at some inscribed polygons. And normally, if we were in class together, we would go ahead and create a quadrilateral inside this circle. And being an inscribed shape, look at these theorems that we have down here. You've got your right triangle. You're going to see this pretty often because there's a relationship. And I really don't even think that you need this, right? Because the diameter is always going to be the hypotenuse of your right triangle. And it intercepts 180 degrees, so your inscribed angle will always be 90. Like we already saw that happening. So to me, that's kind of like, why is it not a postulate? I don't know why it's a theorem. But anyway, that one's super easy. This one's where I want to focus on with you a little bit. So here's what it looks like to have an inscribed quadrilateral. Now you guys already know how many degrees are inside the quadrilateral. 360, right, my friends? And you know that around the outside of the circle, it's also going to be 360 degrees in the arc measurement. So here's what I want you to learn today. Let's read the theorem real quick, and then you'll see how it makes sense. It says a quadrilateral can be inscribed in a circle if and only if its opposite angles are supplementary. So you hear the biconditional there. Let's just see why the opposite angles are supplementary. I'm going to look at angle F. So angle F intercepts arc EHG. And then looking at its opposite angle, angle EHG intercepts the rest of the circle. So here's the thing. These two angles together intercept the entire circle. And when you think about it, if there's 360 degrees in a circle, then the sum of these two angles has to equal to half the whole entire circle because they're inscribed angles. That makes sense to you guys? If you don't like the way I'm explaining it, then go ahead and create one and measure the angles and you'll see it works every single time. But this is a biconditional statement. So if you see that you have inscribed angles in a quadrilateral in a circle, then you know they're supplementary. If you see that they're supplementary, then you know you have a quadrilateral inscribed. Here's what some of your examples are going to look like. I'm going to let you try these out on your own. I don't think they're too bad. So I'm going to give you a moment to do number 1. All right, so did you get 40 degrees? By looking at the picture, you should know that this angle is intercepting half the circle. So this angle is 90 degrees. So you're going to do a 2x plus 10 equals 90 degrees. Please tell me you subtracted the 10 so that 2x equals 80 and x equals 40 degrees. All right, so for number 2, x should be easy for you to find. Yep, it's 90 degrees. So once you know that this is a right angle, you know that y plus 35 is going to equal the complementary, right? Those are complementary to each other. So y plus 35 equals 90 degrees also. So y is going to equal 55 degrees. All right, last one down at the bottom here. I'm going to give you a moment. I want you to go ahead to find x and y on your own. All right, doesn't really matter which one you do first, but the idea is that they're supplementary to each other. Your opposite angles are supplementary to one another. Now, this is just any other quadrilateral. It's not necessarily a parallelogram, so don't try to like work that in the mold here. But it's just a four-sided figure, and any four-sided figure it's going to work for. So first of all, I noticed right away that with y, the opposite angle is 100. So if I know y plus 100 equals 180, y must equal 80 degrees. Did you get that one? And then I noticed, now you can do these two different ways, right? If you know that there's 75 degrees used up here, how much is left for this angle if they're supplementary? This is 105, right? Doesn't 105 equal 75? So you can do it that way if you want. I like that way. So x plus 35 equals 105. And then when you subtract the 35, x is 70 degrees. Okie dokie. So there you have it, inscribed angles, inscribed polygons. Your next worksheets, I believe they are section 10.4, which again doesn't correlate to your book, but that's just how they're labeled. And find them on my CCA. And the next live class, we're going to grade them, and then you'll upload the graded ones. All right. God bless you guys. Have a wonderful day. Bye.